Welcome everybody to this second edition of the WiRE conference in Women in Renewable Energy. We will have a very interesting list of speakers today, and this is organized by the second Severo Ochoa program here at my research institute, the Catalan Institute of Nanoscience and Nanotechnology, and the co-organizer is Professor Sakia Kafafi. Sakia, can you talk? Can you say something, please?
Good morning, everybody. Buenos dias, bonjour, buongiorno, bon dia, guten morgen, sabah al khair. Sabah al khair is good morning in Arabic, which means a morning of peace and prosperity. Greetings from Washington, D.C. I hope that this message finds you all well under these unprecedented, challenging times due to COVID-19. I'm Sakia Kafafi, and I'm chairing this workshop on women in renewable energy with Professor Monica Lira Cantu, who will be making a few remarks shortly after mine. Let me just tell you very quickly how this conference started. It was in a way thanks to Monica. About 2.5 years ago, I was invited to give a keynote talk, an opening talk at a conference that Monica was organizing in beautiful Barcelona, Spain. And I noticed there were lots of women scientists, young women scientists very active in the field of renewable energy. In particular, this was looking at the stability of organic photovoltaics. So while I was attending this beautiful workshop, excellent workshop that Monica has organized in Barcelona, the idea came to me, why don't we start organizing a conference, all women speakers in renewable energy? Because in 2018, there were quite a few active women researchers all over the world in renewable energy. And this is in contrast to when I started my career. Often I was the only woman in the room. So we came a long way, baby, as they say, for the cigarette act, but this is for scientists, which is much more useful than smoking cigarettes for women. Anyway, so I proposed to Monica to join me in organizing this WiRE, Women in Renewable Energy. And the first one was held in beautiful San Diego in August 2019, was part of the meeting of organic photonic and electronics. And we had a very good meeting there. And Monica promised that the next meeting will be in Barcelona. And if it weren't for COVID, we will all be meeting in beautiful Barcelona again. Hopefully, maybe in conference of WiRE 2021, we will be meeting in Barcelona. And I would like to dedicate this Women in Renewable Energy to all our daughters and granddaughters. And I have 2 daughters and 2 beautiful granddaughters. One is only 2 years old and one is 10-month-old, Amali and Lina, which means my hope and ours in Arabic. We are very fortunate today to have as invited speakers 8 women luminaries working in different areas of renewable energy. These women, scientists and engineers, represent educational and research institutions from 6 countries: Australia, Switzerland, the United States of America, Saudi Arabia, the Netherlands, and Italy, and 4 different continents: Australia, Europe, North America, and Asia. Monica?
Thank you, Sakia. Thank you very much for a very nice introduction and for welcome all of our attendees. It's very nice to remember how all this started, and I really hope that we can organize many more WiRE conferences in next years in different countries around the world. At least we have a possibility to do it in Brazil and in Denmark in the following years. So before we start, I want to tell all the attendees some instructions. So we have the speaker. After the speaker, we will have a question and answer section. But during the talk, you can write the questions that you want for the speaker at the bottom of the screen. You can see this label that says Q&A. And Sakia will read the questions for the speaker at the end, okay? Then we will have also the round table. We will give a short introduction how to do the interaction with the speakers right before the event, and also for the posters. For the poster, we have 20 posters, and each one of them has their own link. You will receive the link through the chat of the Zoom, so only persons who register can enter the rooms, okay? If you have any question, please use also the chat to ask us anything. So I will leave you with our first speaker, and Sakia, do you want to introduce our first speaker?
Yes, it will be my honor and my pleasure. It gives me a great pleasure to introduce our first invited speaker, Professor Anita Ho-Baillie. She is the Hooke Chair of Nanoscience at the University of Sydney in Australia, and she's staying up very late to give her talk. Thank you, Anita, for that. The title of her talk is Durable Perovskite Solar Cells. Anita?
Thanks for introducing me, Sakia. Wondering if people can see my screen. What are people seeing? Okay, hang on, I'll do it again. Sorry about that. Share screen. Okay. So, have I got the PowerPoint presentation in the right mode?
Yes.
Oh, good, excellent. So thank you so much for inviting me to this event, and I'm very honored to be able to give a talk. And I thought, since I'm the first speaker, I'll sort of just have the narrative out. So why are we doing renewables? That's because our Earth is warming up, and basically we run out of our quota for carbon dioxide emissions. So unfortunately, we're heading towards the 1.5 degrees Celsius global warming. So what I would like to draw your attention to is this person, Professor Hans Schellnhuber. He was in Australia in 2011, and he was asked by a bunch of journalists, what is the difference between 2 degrees of warming as opposed to 4 degrees? And he said the difference is human civilization. So I guess we got to be very clear, and I'm sure the young people are very aware that if we keep emitting carbon emissions, we are going to get hotter and hotter. Not only will we destroy the environment, we'll actually self-destruct. But fortunately, since 2013, we are actually installing more renewable per year than coal, natural gas and oil combined. So that's really good news. And if you look at the share of renewables, which is the yellow square, it's been increasing by 11% for the last 3 years, since 2016 to 2019. And for photovoltaics, a huge increase, increased by 87% just in 3 years' time. So there was a report that came out by the International Energy Agency, and they talk about that solar will be the new king. And I got a call by the Australian Broadcasting Company and asked me if I can give my comment, and within 15 minutes, or a very short notice, and I said, yes, no problem. But it was interesting, no matter how much I say about solar, they still drag me into the government policy about gas. So yeah, so there's a lot of work to be done out there that will change the minds of a lot of the conservative government politicians. Fortunately, we are doing really well. I was going to show the number of jobs in renewables. It has increased from 7 million to 11 million globally. And in the world, 1/3 of the renewable jobs go to photovoltaics. So yeah, I'm very pleased to be able to in this field and be able to train students and educate students in the field. So metal halide perovskite is the material system that I work with. So I came from a silicon background, but I switched to perovskite. And why? And that's because the material is quite amazing. So it's got a crystal structure shown here, and it's got a general formula of ABX. So A is a cation, B is a metal, which can be lead, tin, germanium, or a mixture of those. And the X site is for the halide. So it's the second last column of the periodic table. So it's iodide, bromide, chlorine, or fluoride. Am I supposed to respond to Monica or not really? Okay, so I keep going.
Yes, please.
So, so perovskite's got exceptional optoelectronic properties, and it's got really good absorption coefficients. So therefore, we can make it into thin films, and it can absorb light as efficient as silicon, but it's 200 to 500 times thinner. Also, we can tune the band gap. So if you look at the right-hand side, you can see that by changing the A side, which can be methyl ammonium or formidinium, I can never pronounce that properly, or cesium, we can change the band gap. We can also change the B site to lead or tin or a mixture of those, and also with iodine or bromine or a mixture of those. So basically my research group has tried almost every combination in this table. So now the sort of the hot or the state-of-the-art material is usually cesium, FAMA. Anyway, and I'll show you what their stability is like. Okay, so also, if you look at the solar spectrum, I use this Goldilocks and the three bears, or Goldilocks and the three solar cells, as an analogy to explain tandem. So for solar cells, if you have photon energy that is lower than the band gap, the solar cell doesn't do anything. The light just goes straight through. And if you have photon energy that is higher than the band gap, the light is absorbed and is useful electrical energy. But the excess energy will be turned into heat, so sort of wasted. So if you have the photon energy the same as the band gap, you'll have light being absorbed efficiently. So it's like Goldilocks seeing the bed that is just right, or the porridge, a bowl of porridge that is just right. So you can see that there are some solar cells, for example, silicon. Most of the time for silicon, the photon energy is higher than the band gap, and therefore you have a lot of waste heat. So the idea of tandem is to stack all the materials, stack the materials with different band gaps so that each of them does its job properly. So you have Goldilocks that can sleep in a big bed, a Goldilocks that can sleep in a middle-sized bed, and the Goldilocks that can sleep in the smaller sized bed. And then you stack them together and you can see the efficiency keeps increasing if you increase the number of junction. But as you increase the number of junction to say beyond 5 or even beyond 4, beyond 3, you'll see that the increase is marginal. So that's the beauty of perovskite, because you can tune the band gap, you can actually use them for tandem cells. Another beauty of perovskite is, see if I can, oh, okay, I can't. So I was supposed to show you a video of how the student can make the perovskite film very quickly using drop and spin coat process, or even the spray process. So this spray gun is used for artists. So we just buy it from the artist shop, and we managed to make cesium lead iodide bromide cell. So you can see the metal halide perovskite is very versatile in terms of manufacturing methods. So again, our group has basically tried every method except the roll-to-roll printing, which got the advantage of high throughput. So you can print it like newspaper. And also it's got very flexible cell structure. So essentially every perovskite cell, you need a superstrate, which is a substrate for you to deposit the material on. And then you turn it upside down and it's transparent so that the light can get through. Then it's got a transparent conductive layer as an electrode, and at the back you can have an electrode that is opaque or transparent. And you always have electron transport layer and hole transport layer. So hole is basically the positive charge. And in the middle, you have the perovskite, that is the photoactive absorber. So you can swap those two layers if you want. The superstrate can be glass or a flexible film, and the transparent conductive layer can be ITO, FTO, graphene, thin gold. So what makes perovskite so attractive is not only is it easy to make, its performance has increased double in 10 years as compared to the sort of incumbent technology that took 40 years for the efficiency to double. So it's got high power to weight ratio, is flexible, and sort of opens up opportunities for the cells to be applied everywhere. However, perovskite's got a problem. It's easy to make, but it can be easily decompose as well under, for example, thermal and moisture. So the incumbent silicon module has to last for 25 years. Product warranty is around 15 years. And how about perovskites? Well, the idea is to make it more durable. In our case, we want to make it durable under moisture and thermal stress to start with. So I'm going to talk about some of the glass encapsulation reported for perovskite cells, some of the chemical analysis used to understand decomposition, and the encapsulation techniques that is reported by us and why they work. So most of the groups report the use of butyl rubber as an edge sealant. So they either just seal the edge without any encapsulant, or they edge seal with an encapsulant, either EVA or PO, polyolefin layer. Some of them use UV epoxy with a desiccant, like a water absorbing material. So these 6 reports, they managed to pass, and I say quotation mark pass, because they managed to maintain the cell efficiency, which is less than 10% after the IEC test. So the IEC standards have become stricter since. So you have to maintain 5% of the initial performance. For dam heat is after 1,000 hours of 85 degrees Celsius and 85% relative humidity. For the thermal cycling is 200 cycles between -40 and plus 85 degrees. And with humidity freeze, you have to do 10 thermal cycles first and then 30 humidity freeze cycles, where you just introduce the cell to dam heat. And if there's any moisture ingress into the cell, it will crystallize when you freeze it, and it will wreck the edge or the cell if there's moisture ingress. Okay, so what is our strategy of stabilizing cells? Well, to stabilize the cell, we want to understand how it degrades first. So we use gas chromatography mass spectrometry to find out the degradation products and thereby the degradation mechanism. So GCMS GC is used to separate a chemical mixture, and MS is used to identify the components. So they've been used for developing pharmaceuticals, detecting explosives, testing drug cheats, or analyzing soil samples from Mars. So in this case, we use it for perovskites. So I remember a professor said to me, "Oh, wow, like never thought that you can do that." Or actually didn't cross our mind because we use GCMS a lot for our other work. So anyway, in our case, we didn't just look at methyl ammonium lead iodide. We actually look at the mixed cation, mixed halide perovskites. So is there a formula? Yeah, we look at the 85% FAI and 15% MABR mixture. So what we do is we heat up the precursors. So we heat up the MAI, FAI, MABR, and the mixture of the precursors at 350 degrees, 140 degrees, and 85 degrees for different times. So high temperature, we don't heat it as much because they don't operate at 350 degrees in the field. 85 degrees, we heat it for 100 hours because that's the likely temperature they will operate in the field, even though they don't go for 100 hours, but why not? We're going to torture it anyway. So let's see what happens. So what we see is for MAI, the signature product is CH3I. For the FAI, the signature product is HCN at high temperature. And fortunately, at low temperature, is not hydrogen cyanide. For MABR, we get CH3BR. And for the mixture, you'll have the combination of both. And I'll explain a bit later. So anyway, from these signature products, we can arrive at the decomposition reactions of 1, 2, 3, and equations 4 are reversible. We also have the CH3NHT product. It's the intermediate product of MA, but it can hardly be detected. And again, as I said, HCN is detected at high temperature, but not at low temperature. Now, interestingly, when we mix the precursors, we found that we have CH3I. So if you remember, CH3I is the signature product of MAI, but here we've got FAI and MABR. So there are two explanations. So one is, well, if you're going to mix the precursors, it's going to become a solid solution, which is valid for high temperature. But how about 85 degrees? Well, so we think it's represented by equation 5, where the CH3I is produced by the methylamine from 4B, equation 4B, which came from MABR, and reacting with HI, which came from equation 2, which came from FAI. Other things that we found is we always found ammonia in everything, in every precursor, but it's the lowest from MABR. So what it say is MABR is more stable. But you can see that at low temperature, you don't find ammonia from MAI or MABR, and that's probably due to the production of ammonia salt at low temperature. And therefore, because MAI and MABR doesn't contribute to NH3, you'll see the product. So you will see the NH3 product from FAI and the mixture is the same because that doesn't contribute to NH3 production. And we also look at cesium, and yay, there's no outgassing from cesium. So you can tell that if perovskite has cesium in it, it will be, not outgassing. Another thing that I didn't mention here is we found that if you have FAI or FAI, as soon as you put MABR in there, you will sort of make the precursor less stable. Okay, so what do we do with the information? You have the signature products. So they're like fingerprints that you can use to evaluate the effectiveness of the encapsulation schemes that we developed. So we use low-cost polymer, which is PIB or PO, and we use two techniques. One is a blanket encapsulation. You can see the polymer covering the entire cell, or we use the edge seal. You have the polymer just going around the cell, and therefore you have a void there. And we use metal-free feed through. So we're relying on the FTO to do the feed through. Then we we stress the test structure as well as the encapsulated cell. So you see the test structure here without the encapsulant, and then the full cell with the a blanket encapsulation and the edge seal, the void. So we can see two things. PTAA, which is the HTM of the cell, is quite stable. There's no outgassing. And cesium FAMA outgas 5 times less than FAMA. So what do we find? What else do we find? Well, PO is more effective than PIB in suppressing the CH3I and CH3BR. So you can see from here, just all this is in the way. So you can see that these peaks are lower, sorry, the cesium is better. And also the PO there, yeah, you can see there's hardly any peaks there. but PO is more permeable to NH3 than PIB, or maybe PO absorbs more NH3. So what we find is, if we put a glass on top of the polymer, there's no outgassing. So that one with the glass, you can see there's no outgassing. The H-seal one, you can see a little bit. So this represents the H-seal. You can see a little bit of CH3I coming out. So what's the conclusion is, we found that the encapsulation, the polymer glass encapsulation does two things. One is it stops the moisture from going in. Two is there's no void. So when you use the blanket, it takes away the void, and therefore it takes away the opportunity for the perovskite to outgas, and therefore it stops the decomposition reaction from proceeding. And by blanket encapsulating the cell with glass, we were able to exceed the requirement of the IEC standard. So the IEC standard is you have to maintain 95% of the initial efficiency after 1,000 hours. We were able to exceed by 700 hours. Also, the IEC requirement is we have to be able to maintain the efficiency at 95% after 30 humidity-free cycles, but we're able to do 75. So that's it for my talk. And thanks very much for listening.
Anita, thank you very much. It was a very interesting talk, especially that my expertise in stability of solar cells. We have two questions. Can you see it in the Q&A label?
Yeah, so from Emily. Do you know there's with another stressor other than heat? Yes, yes, we're doing the experiments right now. So yes, we're doing it, and we're looking at different cell structure too, to see what the response is. So hopefully some will be more like stable than the other. Carla, what method does Anita, employ to calculate the band gap of the ABX materials? The most, I think, reliable way is actually make a solar cell, and then you measure the EQE, and then you do a differential of the EQE, and when you will see the peak, which is the inflection of the EQE, and that's I found the most reliable way of, we call it the absorption threshold. But that's, for me, is sort of the most reliable way of knowing when the absorption is. So for device, that's what we want to know. So yeah, I know there's like difference between optical band gap and electronic band gap. Yeah, but at the device level, the best way is to look at the EQE and the differential of the EQE.
Thank you, Anita. I have one question.
Mm-hmm.
What do you know? How is the bonding between the polymer, the PTAA, to the perovskite, or maybe to the whole transport material of the? What is the binding type of bonding that makes this polymer so good for stability?
Oh, okay. So it's actually not the polymer per se, because you can see that without the glass, you can still see some of the signature products coming out. And by the way, we found the PIB and PO can outgas as well. So they either block the outgassing or they actually absorb the gases, and then like a sponge. But it's really the combination of the polymer and the glass that do the job well. And it has to be covering the entire cell, so there's no void for the outgassing to occur.
Okay, very interesting. I think we don't have any more questions, but anybody can contact you and...
Sakir's got a question. We can't say no to her.
Okay. There's another question?
Yes. Very nice, Anita. A fantastic talk. I have a question. When you put the formula H3C3N3, do you mean 3 molecules of HCN?
I need to talk to my student about that because I'm not a chemist.
Because I'm a chemist and I don't understand what that means.
Mm-hmm.
Okay.
So that's what he finds.
Well, but you know, I mean, why not write 3HCN? 3HCN. I don't understand it. I would send me the answer. Okay, thank you very much. Excellent talk.
Thank you.
So I would like to thank you, Anita, very much for your talk. I have to say to everybody that right now is like 1 a.m. for you, right, in Australia? We really
12:30,
appreciate that you're here
12:25.
with us. Okay. Thank you
It's
very much,
Saturday.
Anita.
It's Saturday.
Okay.
Good.
Thank you very much, Anita.